All right. So, welcome to another lecture of probability and statistics. So, lecture number 4 for our 13, I think. So, we are 1/3 already, almost. Go. So, today is random numbers and expectation values and some distribution. So, we start looking at how a probability distribution look like before, right? We have this uniform distribution, and now we're going to go to ones that actually have a shape, and these are the Bernoulli distribution, the binomial. We start with that simple one, and then we go to the Poisson distribution, and for all of them we're going to see how we can parameterize it, these distributions, and we use the expected value, the variance, and the standard deviation as parameters that define a distribution. So let's start. So last week we already defined what the expected value of a random variable or random number was, and if you remember, that was the summation of the event to happen times the probability of that event to happen. And if you have many different realizations that are possible, so you sum up over all the realizations, right? And if you remember, we have the die, and if you toss the die, you can have a 1, 2, 3, 4, 5, 6. And the probability that one of these spaces show up is 1/6, right? So what you was doing is multiplying 1 times 1/6 plus 2 times 1/6 and so on. And then you get something like 3.5, which we saw that it's not an actual realization, but this is particular for the expected value. So it's going to be something in between or a realization itself. So, also, we have been using already the expected value when we were talking about a fair game or unfair game, right? That what was your expected gain or lose? And we remember that when the expected value was around 0, the game was fair, and if it's less than 0, you will be losing money, and if more than 0, you will be earning money, right? So we were already knowing what the expected value is and how actually you can use it. So today and the expected value itself, I think one of you already noticed that it's basically in the long term. So if you repeat your experiment many times, it converts to the average, right? So kind of where your values will sit more or less, right? It's like a value that is, all the values will be summed around that number, right? That's the expected value. But of course, not all the values will be exactly that number, expected value, because it's actually expected, but not has to be the actual value. But they will fluctuate around this number. And you want to measure that fluctuation, right? How much these values change over this average. And then you use something that is called the variance of that data, right? So if I can be more explicit, let's say that you have some measurements of anything, and you have an expected value that you have in this case, for example, 3.5 for the dice. Then when you throw a die, it will be something like, sometimes you get a 4, sometimes you get a 1, sometimes you get a 3, sometimes you get a 2. So it will be some values that are fluctuating around that number. And the fluctuation, how large the fluctuation or how small the fluctuation are measured by the variance. And the variance is nothing but an expected value itself. But instead of expecting the value to happen, you want to see what is the expected difference between each of these points and this mean or expected value mu. Okay? So if the formula is the same as expected value, right? But now you have the difference of each of these individual points or realization that you will have minus your expected value, mu. Okay? And you notice that there is a square here, and this serves two purposes. One is to get rid of if it's negative or positive, the difference, because you are actually only interested in the difference, right? And how large the difference is. And also it serves as a kind of an amplification. Because if the difference is too small, the square will be even more smaller. And if the difference is too large, the square of that will be even larger. So that's kind of it helps to zoom in on the data, let's say, or zoom out on the data. So, and then you multiply by the probability of this to happen, right? So each realization to happen. And that's the pure definition of variance. If you ever have any class that talks about variance, maybe you encounter this, but it's not sometimes the way that you present it. And you can take this also, and this is important because it will help us later for some derivation. The variance is basically the expected value of the random variable to take any realization minus the expected value to the square. Okay? So you can actually see it like that way. Again, it's the difference between each point and the mean amplified. Right? So usually the variance is written as a sigma square, and it's written as sigma square to kind of emphasize the square thing here, right? And then if you take the square root of the variance, you get the standard deviation, which is one of the most, the average and the standard deviation, I think, are the most known parameters for any distribution of any data, right? And the idea of the standard deviation, you will take the square root, and then this amplification is wash it away, right? And then you get, again, in the scale of your data. That's all. So standard deviation is something that that is very useful when you describe. You are describing a distribution here. Okay? Good. So, what is the standard deviation the variance good for? That's what I want you to say. That the expected value is kind of at the gravity center where the distribution sits on, and then it will be, fluctuating from that to the other. So, for example, here you have two distributions that have roughly the same expected value, around 4, right? But you can see that the dispersion is larger for the left one than to the right one, right? So these two distributions, for example, will have a different variance with the same expected value, okay? Just for you to have it like graphically. And if you happen to have a distribution that is in a bell shape, what's called sometimes Gaussian distribution, or norm, you will see that the normal distribution has this shape. Exactly, if you add one standard deviation to the average, or subtract one standard deviation to the average, in total you will have 68 of the point already there, right, of the distribution. And then if you go 2 sigmas, you will have 96 or 98, I don't remember, 96, 98, or more close to 98. And then if you go 3 standard deviations, you already have 99% of the point in the distribution. We'll see this later. But these are for you to, I don't know, have a quick overview of what mean and or expected value of variance means and how this can be useful. All right? Good. So, examples as always. You remember that if you toss the die, we said the expected value was 3.5, which was not a realization actually. Then let's calculate the variance of this die throwing one way. So you will have our dice as always, right? And you will have 1, I don't know, 3 on the other side, and 2 and 5, no, 3 and 6, 1 and 6, 2 and 5, and so on, right? And then you have to take each of these faces and put it here, right? And then subtract it to the expected value we already have calculated and multiply by the probability for this to happen. That's always 1/6. For the dice, it's pretty simple. So that's basically what's done here. If you sum 1 plus 2 plus 3 plus 4 plus 5 and 6, you get 21. 21 is the 21/6 is the 3.5. This is 3.5. If you now just do the subtraction of 1 minus, you get 1, 2, 3, 4, 5, 6, 6. If you subtract to the mean, or the expected value, and you multiply by 1/6, which is the probability. You get all this part of the equation here, and then you sum it all together, and you get a variance of 2.916 periodic, whatever. Right? So this is the flat distribution of toast in a die is expected value of 3.5 and variance of 2.91. Okay, meaning something, whatever. And the standard deviation will be the square root of that, which is 1.7. All right, nothing really, so amazing here. What happens if you throw the die 2 times now? So now our omega, remember, is 36 because before was 8, right? Now 6 to the 2 is our all the possibility, because you have 2 dice that have 6 possibilities each, right? And then you do the same. You, for the expected value, you multiply, so you can get 1, 1, right? This is the expected value. 1, 1 is 2. Yeah, exactly. Then you can get 1 and 2, and you get 3, and so on and so forth. So remember that you have 2 dice now. We have done this before. And if you sum up, your expected value is exactly the double of having only 1 dice. So before was 3.5, now it's 7. Okay, makes sense. You expect that if you throw the die 1 time, the expected value is 3.5. If you throw it 2 times, yeah, it should be 7, right? At least it makes sense. What happens with the variance? If you plug in all the numbers, as I say, for each of the dice and the expected value, and you multiply by the probability, that is always 1/36, you get 5.83. The standard deviation, or the variance for throwing 1 dice, was 2.9. So it's not exactly the double. And this is something particular of the variance, and it cannot make sense in reality, because remember that we want to estimate, what we are doing is estimating the jitter, or the variance around the expected value. So the more information you have, the less should be the variability, because you know more about the system. So if you throw the die 3 times, the variance will be even lower. If you throw it 4 times, the variance should be lower until you throw it so many times that you get to the expected value. Okay, that's the idea always of the variance and the standard deviation. So if you calculate the standard deviation, also it's not exactly the double, but it's lower than that. Okay, that is true to anything. So the more you know, the less uncertainty you have about anything, the less should be the variability that you have. Okay, that is the concept. So I say that we can use a trick to calculate the variance, because as you can see already, this is mess here. As you can see already, plugging all the numbers is quite tedious and it's not so nice. So you can define the variance as the expected value of the random variable squared minus the expected value squared. Okay? And with that, it makes the calculation a little bit simpler, because usually you already have calculated the expected value, and you only have to calculate expected value of the same variable square. So in this case, the expected value of the square would be always is we are talking about having only 1 die here. Okay? So we will have 1 square, 2 square, 3 square, 4 square, 6, 5, and 6 square. Okay? And then you divide by the probability, because you're doing here. And then the expected value of the variable square is 91/6. So now you have done this part. The other part would be the expected value square. We already have calculated that. It was 3.5, or you can actually redone it if you want. It will be this part, and then you square it, and you did that. And then if you subtract you get the same values than before. All right? You will see that this is useful. I will try to remember this trick because you will find it handy at some point. Okay, good, simple stuff. All right, with that, we now have three parameters that we know how to characterize distribution. So expected value, variance, and standard deviation. One is where the distribution will kind of sit in, and then the variance and the standard deviation will be how it's spread around this expected value. All right? Let's start with some distribution that you can actually use those. The very first distribution that you're probably going to encounter if you look at probability is the Bernoulli distribution. The Bernoulli distribution comes from what is called the Bernoulli experiment, right? And it was developed by Bernoulli, with no surprise. And the idea is that you have an experiment that has only two outcomes: 0, 1, fail, and success, death, and alive, whatever you want to call it. Only two possibilities, and you run it one time. It's like, for example, tossing the coin. From one time you have 0, 1, tail, or head, or whatever you want to call it, right? And that's what distribution models. When we're talking about distribution, we are modeling an experiment, we're modeling a set of data. That's the idea of the distribution. We are modeling with a probability distribution, which is a probabilistic model, if you want to call it. So you want to have a distribution that probabilistically will fit the data. In this case, the data will be outcomes from two possible options. So you have two options. The probability of X to become 1, or the probability of X to become 0. And one is P, we call it P just because we are, I don't know, we are in love with this letter, but it could be any letter. P is P. And then the other will be Q. And in this particular case, Q is 1 minus P, because you have only two possibilities. The sum of the probability has to be equal to 1 because of Komarov, right? So it's a complementary always. So it makes the distribution quite easy to deal with. So what would be the expected value of this nice distribution, the Bernoulli distribution? So you will have to calculate the event to happen times the probability of that event to happen, right? As always. So what are the two events? You get a 0 or you get a 1. These are the two things that will happen. So then the event of 1 times the probability of the event to be a 1 is P, as we define it here, right? Plus the event 0 times the probability of this to happen, which is Q, or 1 minus P. And 0 times anything is 0, so this guy goes out, and then you get that the expected value of the Bernoulli distribution is just P. Okay? Nothing really excited here, but it is what it is. The variance, the same. We can, again, check that I use sometimes mu and sometimes E, because they are, in the literature, are quite equivalent, right? Some people call it mu, some people call it expected value. So the variance, we know that we can calculate it by the expected value of the random variable squared, or the expected value of the variable squared. And then, if you get the expected value of x squared, would be like putting a square here and putting a square here. Right? So 1 to the square is 1, 0 to the square is 0. So again, P, expected value of x squared is again P, right? And then the expected value, which is P squared, is P squared. Right? So at the end, if you call Q equal to 1 minus P, and you put it here, you get that the variance of a Bernoulli distribution is P times Q. That's it. Really simple equation to remember, right? And could be give you some points in the exam. So I will start thinking about P and Q's from now on. So simple, P, Q, right? And then what will be the standard deviation of this? Just the square root of that, right? Simple, that's that. Good. So that is when you have one event. You have thoughts in a call one time, you get what is called a Bernoulli effect. What happens if you continue doing this for n times? Then you have to model in another way, right? And that's what the binomial distribution comes in. And basically, a binomial distribution is from an experiment of repeating many times a Bernoulli effect, okay? Bernoulli distribution. So, again, we are talking about two types of outcomes, 0 or 1. So A and A complementary, like put it here, death and life, success or not success, whatever, failure or success. So, like flipping the coin many times, like I said here, or for example, drawing balls from a pot, and you can replace them, and you have two colors, black and white, for example, or red and blue. Okay, that could also be an example of Bernoulli and binomial distribution. So, for example, let's say that you have one pot and you have 5 white balls and 3 black balls, right? And then you can draw one and see the color and put it back. Okay, so every time you draw one ball from this pot is independent from the previous one because you have to throw it again back. And in some way you shake the pot so you don't get always the same, right? So you get two disjoint results, right? And then if it was one time, you will get the probability, for example, of getting let's say that A is white and A complement is black. So the probability to get a white would be 5 over 8 because you have 5 white over 5 plus 3 in total 8, right? And then the probability to get a black would be 3 over 8 because you have only 3 black and 8 in total. So that defines your P and Q. And you could already have calculated P, A complement by 1 minus P, right? This guy here is 1 minus P, right? As we said before. Okay, so let's generalize this. Let's say that you want to generalize it for any event that happened, and let's say that you have n balls in total, and from this n balls, m are white. So n minus n would be black, right? So if you have 100 balls and 50 are, or 30 are white, 100 minus 30, 70 are black. Fair enough, right? So then the probability of getting a white will be m over n, so the number of white divided by the number of total. And the probability of getting a black will be n minus m divided by n. Okay? Simple as that. So now let's say that you repeat that, you draw the ball many times, and I call it n times. Don't confuse. N is different from n. So n will be the number of times I have getting the ball, and large here is the number of balls inside the pot. Okay? It's a different story. So n will be your number of times, and let's say from this n times that you have picked the ball, x gets white, and then n minus x gets black. Okay? Simple as that. So from n times that you have picked the ball, you see it, x times are white, and n minus x will be black. Okay? Then, then you maybe you're interested in the probability to get a white, right? Because you're curious. So what is the probability of from n times that you have picked a ball? What will the probability to get a white? Then you can calculate the intersection between getting a white and not getting a white, which will be this case. And since you always replace the ball and you shake it in some way, the one that you get now has nothing to do with the previous one, and it has nothing to do with the future ones. So they are stochastically independent. So we can actually intersection calculate the multiplication of the probability separate, right? And then this tells us that basically you will have x times the probability p, right? X times, so x times are the times that you get a white, multiply x time, because you get it x time, right? And then n minus x time would be, so this will be the white, or the A if you want. And then n minus x time you will get not A, not a Y, right? And if you put it together, it would be, the first bracket will be p to the x, and then the other will be p to, q to the n minus x, right? Because remember, p is the probability of getting the y, and q is the probability of not getting a y, right? So that is that, right? So, but this is, this will be just for getting a white, right? Just this case, this particular case, will be just to get, what is the probability to get a white, right? And what happens with the other combination? That you get a white and you get a, for example, a black, and you get a black and you get a white, and you get two white, and you get two black, and so on and so forth. Or that the first one is a black, and the number 10 is a white, so there are many combinations, right? That you could put it in this way, and x minus n minus x will change. So that's when it comes to play what we were seeing a few weeks ago, the permutation, right? So you have to permute the same structure, this structure, in a way that models all the alternatives that you could have, black and white, right, with two outcomes. And remember that we have these two things. One, that two questions when we were looking at the permutations or the combinations, combinatories that we were talking. One is, are they elements different from each other? And can you differentiate, can the different element occur more than one time, right? So the first one is referring to, do you have a clear black and white, or you have maybe three blues, three red, and then between the blue you cannot differentiate them, okay? The second one is replace it or not taking now into account, right? So in most of the cases, Q1, or question 1 is usually real, yes, and the second question is answered as no. In our case, the first question is no, because they are not different in each other. Because you have black and white, but you have n, or yeah, you have n white and n minus n black, okay? And between those black and white, you cannot really, between the black, you cannot, they don't have a number. It's not black number 1, black number 2, and black number 3. It's the same for the white. So you can actually not differentiate them. And they do not occur two times because we make a replacement of the ball. Okay? So then you come up to, you have to do the combination where we have, remember, a factorial corrected by each of the times that you have picked the ball from. This is just for you to have a graph on this. So for example, if you have a shelf and there is 5 different books, right? So since they are different and you don't care about the order, so the way that you can arrange this book in the shelf would be 5 factorial. Okay? Now, if you have 6 balls in a pot again, and 3 are white and 2 are black, right, say, and 1 is gray, then you cannot differentiate between the blacks, the white, the black, and maybe you can differentiate between 1 gray, right? So you have to correct, and that's why you divide the factorial by the number of factorial multiplied. So, but I don't want to get you away from the binomial distribution. So again, let's say that we have n event and x were black, were white, and n minus x are black. Then, in our case, we use what we saw before, the binomial coefficient. That's what it comes to the name of the binomial coefficient, right? How many in how many ways you can order x element from a set of n elements, okay? And that's basically what you're trying to do when I try to model many Bernoulli experiments. This Bernoulli experiment can always be black and white, right? But they can come in different combinations. So if you have n experiment, you wanted to know in how many ways you can accommodate the whites to happen in these n experiments, okay? Because the white will happen at the beginning, at the middle, at the end, at some point, right? But they will be in some way distributed within this n drawing of the board, okay? And that's why you use the binomial coefficient. So basically, if you multiply then our basic frame that we have for what happens when you have the white at the beginning, and you multiply by all the combinations that could happen, then you have the whole package you want. So you have, for each combination, you will have p times q, x and n. So x is the number of white, in this case. N minus x is the number of black. And then how many ways you can arrange this to happen, you do with the binomial coefficient, okay? So basically you are taking into account all the possibilities where the white would show up in the nth drawing of the black, okay? And that basically defines the binomial distribution. So that's the equation for the binomial distribution. And it will change by x and n. Right? It will change by the equation that you do and the number of repeated experiments that you have. So, for example, let's check it out how they look graphically. So, for example, if you have n experiment, and of course, these guys especially will play a role, right? Because if you are talking about flipping a coin, if the coin is fair, you have p equals to 0.5, right? Because you have 50% chances of getting a tail or a head, right? But if in some way it's modified, then you could have, for example, here like 0.1, then q becomes 0.9. And then all the distribution moves to the left, okay? Where the mean or the expected value will be more close to 0 than to the other numbers, okay? If you have, for example, now a probability of 0.5, then it looks really more like a shell, like a bell shell that I was telling you, close to a normal distribution. And the more the n increase, then this will change too, right? And then if you go to the other side, that p becomes higher than 0.5, then you get this q to the right. Okay, that's how a binomial distribution looks like. That's it, nothing really crazy here. So let's do an example. So how we can use the binomial distribution, right? So let's say that we flip in a coin, right? If we flip it one time, what will it be? A Bernoulli experiment, right? But since in this case we want to flip it many times, exactly n times, it becomes a binomial distribution, right? Or a binomial experiment, if you want to call it. And you're interested in the number of occurrence of, let's say, tails, 1, right? So our omega will be all the combinations of 0, 1 in n times of repetitions. So then, like I was saying, every time that you flip a coin, it doesn't have nothing to do with the previous one that we flipped in a coin, and it has nothing to do with the future flipping of the coin. So all the probability of getting a 1 or 0 from flipping to flipping can be multiplied each other to get the whole probability, the intersection of the probability, right? The whole of u. So this can be put in this way to make it more compact, right? With the multiplication operator. And then, so we have 0, 1, then again, we have only P as the probability to get a 1, and Q as the probability to get a 0. Again, 1 minus P is Q. And then you could do the same thing that we did before, right? But since you have n times, you can actually, this is what we did before, right? So, I don't like to do this, to be honest, but it's the x and n minus x here, right? For n times, right? So it's just summation of 1 to n for the probability of getting a 0 or a 1, and if it was 1 here, a 0 here. If it was 0 here, a 1 here. Okay? So that becomes handy because now, let's say that we want to know, we have n equal to 4, so 4 flipping of the coin, and then we are interested of this outcome, 1, 0, 1, 1. Okay? So now we can calculate the probability of this, and what will be. So every time, so you will have P, the probability, right? Is in any way defined. The flipping a coin could be, for example, P equal to 0.5, right? And then you have P to the first event, 1, to the second event, 0, to the third and the fourth event, right? Also summated together. Then 1 minus Q, 1 minus P or Q, if you want to call it, to the difference between 1 minus the event. So 1 minus 1, 1 minus 0, 1 minus 1 again, 1 minus 0. So this is 0, this is 0, this is 0, and then you get just 1 minus P, right? So this becomes 1. And then you have 1, 2, 3, this is a 3, so P, 3 times 1 minus P, okay? And then, depending on your P, that is the probability to get this event, okay, from repeating the coin many times. If you say 0.5, then the probability will be 0.06. If the probability P is 0.1, then you will get a different number, okay? So that's the way to calculate, for example, a certain event, a certain series of events to happen when you have only 2 outcomes. All right, so let's see how the expected value and the variance look like. For the expected value, in this case, would be the summation of the event to happen, right? And then we know that the expected value of x is equal to the expected value of the summation of the partition, as we have seen before. Then you can take away the summation outside, and then you have the sum of all the expected value. And the expected value of each of these are the expected value of a Bernoulli experiment, which was P. And if you have n experiment, it makes an n Bernoulli experiment, so sum it together will have n times P as expected value for a binomial distribution. Okay? So the Bernoulli experiment, the expected value was P. If you repeat n times the Bernoulli experiment, you get a binomial distribution with an expected value of n times P. Okay? That is simple to remember too. Okay. So let's have now, and this is another on the side thing because it's useful for the next thing to do. Let's see that you have a function g that maps from the real to the real numbers, and g of x is a discrete random number. Then the expected value of this function is the same as if it was as a random variable x, but you take it the whole function. So the expected value of x is x, the summation, times the probability of x to happen, right? The expected value of the function of this expected value is also the summation of the function valued in that particular value times the probability that you have. right? This is important for when it comes here, because calculating the variance of the binomial distribution is not so straightforward as before. Expected value is simple, n times p. How we calculate the variance? Well, we could take the long path and calculate each of the each of the realization minus the expected value and square it and multiply by the probability of this expected value to happen, this value to happen. Or we can use a formula, right? Which we know we can divide it in this nice format. If we take it like that, then we can start deriving the variance for the binomial distribution. The first one is this one is simple, right? The second one, because the expected value we know that is n times p. So the expected value square will be just n times p squared. Okay, so that is called. We have to calculate this guy. This guy is a little bit more tricky. This is what I say here. Okay, so we have to calculate. We have to come here and do the expected value of x squared will be the same as the expected value of the summation of each of the realizations, this partition of realization is squared. And this will take two kind of output. One that they are equal, the realization, right? And the other that are not equal. So this guy here can be separated in two sums. When xi is equal to xj, and the other one xy is different from xj. Okay? And we're gonna go part by part. For the first one, I repeat here, this is the same as the previous slide, right? For when they are equal, and the summation has to give you 1, right? So the only way that they can be equal and hold that is that x, y, and xj is equal to 1. And then 1 squared, no matter what xj or xy you have, the square will be gone because 1 to the square is 1, no matter which j or I you have. Okay? Then you can also, by additive rules, you can take the summation outside, and then you can simplify this as the summation of expected value multiply each other. Okay? So for each of the I that is equal to 1, there is going to be n minus 1 times that aj is equal to 1, 2. Okay? Because it's a complementary always. So if aj and xi have the probability of p, so the multiplication between them will give you p squared. So what I want you to say with this part is solved here and continue here until here, right? So we always have that guy here. The second can be simplified from the n times p, right? Because this is the effective value of the n times Bernoulli's perimeter. The second, since what we are saying here, that for x times there is a 1, there is n minus 1 time there is a y on the other realization, then you will have n times n minus 1 times p squared. I know that it's not simple to grasp on why x1 and xj can be equal. So now if we replace that, we replace this guy on here, and we already have solved this part, then we can calculate the variance. And if you solve from here to here, you end up in n times p times 1 minus p. And if you know that P is 1 minus Q, then you can also plug that, for example, here. And then what you get is that the variance of the binomial distribution is n times PQ. Okay? So the variance, the expected value of a Bernoulli experiment is P, right? The expected value of a binomial distribution is n times P. Okay? And the variance of the binomial distribution is n times P times Q. That's it. As simple as that. And then if you take the square root of that, you get the standard deviation. That's all it is. So now we have parameterized the binomial distribution as well. Let's do a quick example on that. So let's say that you have a die and you toast it 6 times. Yeah? And we are interested in getting what is the probability to get an even result. Okay? So again, it's a Bernoulli experiment, repeated n times because you can get an even or an uneven. No matter that the die has 6 faces. In this case, we're interested in the ones that are even and the ones that are not even. Okay? So let's say that you have a half chances of getting an even or an uneven because it's an honest die. Then you repeat this 100 times, so n is equal to 100 and p is equal to 0.5. Then the expected value we know for the binomial distribution is n times p. Then the expected value is 50. So you have an expected value that from the 100 times that you throw the die, 50 will be uneven and 50 will be even. That's all. And that will have a dispersion of plus minus 25. So you will have, or actually 25, no, the square root of 5, right? So you have 50 in average, that will be even. It could be 55, could be 45, and so on. And that you can actually see it in this graph. So this is plotting the distribution. The mean or the average or the standard or the expected value is 50, and then you will have plus minus, well, it's a little bit more. So 5 would be here. That would be your standard deviation, right? And then 25 would be larger the variance. So you can already see how the dispersion is actually measured on that. Okay? So now, before I jump to the next and the last one of our distribution today, you can notice that this binomial distribution is a nice distribution for 2 outcomes, failure or success, 0 or 1, for any time that you repeat it. But there is a few problems with this distribution. The first problem is you can see that all the parameters that define the distribution depends on n, right? So the more you repeat the experiment, the more the mean, for example, will be shifted to the right, because n times p will be, if the probability is always the same, and you repeat this 100 times, it's not the same as repeating it 1,000 times. Okay? So you will be shifting your distribution to the right. Right? The other problem is to calculate the binomial distribution. What is the formula? Okay. You have to use the binomial coefficient. And it's fine to calculate the binomial coefficient for 5 numbers, 5 out of 10, 2 from 6, 10 from 50, okay? But as the n increase, the binomial distribution gets really hard to calculate, and actually a computer cannot do it at some point, right? So we have a ill thing here with this distribution. So this was already noticed a long time ago. Sorry, I hate to do that. By Poisson. He said, okay, we have the problem. We have the problem that we have a nice distribution that model 2 event, 0, 1, for n repetition, but it becomes a problem when n increases. So he said, and it's even more problematic when the probability of the event to happen is very low. So when you have a very high number of repetition, but the probability to get the event that you want, that you are interested in, is very low, then this distribution of the binomial doesn't work very well, or it's impossible to calculate. So he said there has to be another way to do it, and that's why it comes the Poisson distribution that he developed. And he comes with an approximation of the binomial distribution, and I show you that. So this is what I said. So no worries about that. That's what I was repeating before. So we start from the binomial distribution. That's how he actually developed this. And then let's say that the probability that you are interested in, the probability of nx, they say white ball, is very low, such that it tends to be 0. It's 0.000001, whatever. And we have so much repetition that n's tend to be infinite. Okay, in the string case, right? A very low probability and a very large number of repetitions that you do the experiment. Okay, so there is a very small chances, small probability to get a 1, for example. Okay, in this case. So if there is a very low probability to get a 1, so that such that the probability directly tends to be 0, okay, or x tends to be 0, then we can replace x directly with 0, right? And n will stay n, larger, very large. Then we can get our binomial by Bernoulli experiment modified as 1 minus p over n. Remember that it was p and times 1 minus p, right? But now in this is q, right? But now p becomes, it tends to be 0, so we get only 1 minus p, okay, over there. So we know that the mu is mp, right? So if you first do this, you first multiply this and divide it by n, you multiply the numerator and denominator of p, you make a fraction here, you just multiply by 1, right? Then it becomes np, which is mu, right? And n is n, right? So you have 1 minus mu over n to the power of n. And this is a power series that can be approximated by the exponential function with the exponent to be mu in this case. Okay? This is an approximation, that's what I was saying. So you can model the case that you have very low probability of the event to happen with a very large number of repetition with just saying the exponential to mu. Okay? That's the approximation that we're going to use first. So if you have running this for n equal to infinity, then it will be exactly the exponential to the minus mu. Okay? But in this case, we don't have n equal to infinity as in reality, then we can say that it's an approximation. And there is a rule of thumb that I will let you know soon. When is this valid? Okay, one is really p very low, and one is really n very large that you cannot use the binomial distribution anymore. So, but this is the case where x was equal to 0, so that the probability to get a 1 was really low, right? Now we have to consider all the other possibilities, or the other probabilities, as we did with the binomial distribution, and we do that with the ratio. So the ratio of getting the probability equal to 0 over the ratio of getting the probability equal to 1, okay, for all the cases that you will have. And this is basically the binomial distribution with x equal to k, or with x equal to k minus 1. Okay, so that's the ratio. And if you include here the binomial coefficient, is here and is here, right? This is the binomial distribution coefficient. And then you solve this ratio of p's here, you get that. And then if you solve this, you end up with a number like this. So not much to say. You wanna prove it yourself that this is true, you can do it. But it's just for you to say. So the ratio is basically that number here. So we can use this ratio, right? And plug in here when P tends to be very low and N tends to be to the infinite, then N times P, it will tend to be the expected value, as we always say, right? So as the N becomes very large, the data should converge to the expected value, right? So from here, you can plug P equal to 0, right? And, P equal to 0 when it tends to 0, right? And Q will tend to 1, okay? And then basically 1 minus 0 is 1, and Q is 1, so it's 1 over 1. So at the end, this ratio, in the case of when we are very low probability and a very large N, becomes only mu over K, okay? And then you repeat that for all the combinations that you could have, right? And then you will have basically P0, which was the one that we calculated before, times all the ratio for K event that you could have, and then you end up with the formula for the Poisson distribution, which is exponential to the minus mu multiplied by the ratio of mu over K factorial. Okay? And it becomes an approximation because of this guy, because it's not exactly as we saw the exponential, but it's an approximation. This is, in this case, the sum of the other probability has to become 1. That proves that this distribution is actually a probability distribution. That's nothing really important. So as a recapitulation, even for the Poisson distribution, so we start with a random experiment. 2 outcomes, 1 experiment. Binomial distribution, 2 outcomes, n times the repetition de Bernoulli. Comes Poisson with the problem where the probability is very low and the number of repetitions is very large. It comes Poisson with the approximation, right? And the approximation is defined by our formula of Poisson, and it will have the same expected value as the binomial distribution, which makes sense. That's basically it. And this is our formula for the binomial distribution. The expected value of the variance will be, again, the expected value will be, like I say, the same as the binomial distribution, n times p, and the variance is equal also to the expected value, which this expected value for the Poisson distribution is just called lambda, just for you in the literature. And the standard deviation will be the square root of this lambda. So this is the rule of thumb, and it's not proven here, and I know that there is some problem, but it's again a rule of thumb. So n times p has to be less than 10, and n has to be larger than 1,500 p. Okay? So if you meet these two conditions, then you can switch from a binomial to a Poisson distribution. Okay? It makes sense because it means that the probability has to be very low and the n has to be pretty large to have a value less than 10. And again, n has to be quite large with respect to the probability. Okay? This number 1,500 is the rule, but in itself it makes sense. So what you do is you first check. You first have to have in hand a problem that has 2 outcomes and many repetitions. Then you will have first think, okay, this is a binomial distribution. But I will check this. I will do this number n times p, and I will check 1,000 times p. And if this rule meets, then no, I should better use a Poisson distribution. Okay? Also could happen that you have a problem and you say, okay, it's a binomial, but you cannot even calculate it because, like I said, the coefficient will be too difficult to calculate. Then you go directly to the Poisson distribution. Okay. So as an example here, you can talk about decay, radioactive decay. This is a very common problem for a Poisson distribution. Radioactive decay is, you know, you have a radioactive or any element, each of the atoms in an element will have activity, radioactive activity, and this will decay over time, right? The problem is it decays really slowly, right? And the probability for this to become some threshold, for example, of decay is very low. So you will have to measure many times to get an event that this has decay, right? So it's a typical example of a Poisson distribution, right? So let's say that we are interested on, or that X defines the number of atoms that decay per second, okay? And let's say that the average, lambda gives us the average of the number of decay per second of the element, right? And let's say that we have a material that on average decays 100 atoms per minute, so in 60 seconds, right? And let's say that we are interested on what is the probability to observe more than 2 decays per second. Okay? So in 1 second, how many actual events you will have, right? So our lambda is given, is our average, which is 100, our lambda is not an average. Our lambda is given in this case because we are talking about 2 decays per second, okay? So we are looking at lambda equal to 2, right? To the k, to the 2 to the k over k factorial, right? So now we can plug in the example. So we are interested in observing the probability of observing more than 2 decays, and as usual, we can say the probability of observing less than 2 decays. And that would be the probability of observing 0 decay, 1 decay, or exactly 2 decays, right? And then basically our lambda is 2 always. So this guy will be 2 always. And there will be 2 to the 0, 2 to the 1, and 2 to the 2. And then it's 0 factorial, 1 factorial, 2 factorial. And then if you plug in the numbers, there is a probability of 0.32 to observe more than 2 decay in 1 second for this particular case. And the distribution looks like that. So this is the Poisson distribution for this particular case, which is mainly centered on the 2. All right? Good. And another example, let's say now that we go for the electronic production again. So we are an engineer now. We switch from physics to engineer. And let's say that you produce some device, an electronic device. And you know that in average, there is 1% of defective pieces, right? So you want to actually estimate the probability of delivering an effective piece. This is modeled here in a Poisson distribution because hopefully the probability of having a defect is very low, and hopefully you are very successful businessman or woman, and you have made many of these, millions of this device, and then you have the problem with the n equal to n larger. It will be not the case if you are in your, I don't know, garage, and you are producing one device for your uncle, I don't know. So then what will be the probability to find more than 2 defective parts in a sample of 100? So let's say that you produce 1 million per year, and you take 100 one day, and this sample will show you if it's kind of representative of what you are producing, right? And what is the probability to get 2 defective parts? Then you will have a Poisson distribution, right? So in this case, P is 1/100 because we already know, or we assume, that there is 1% defective pieces that you produce, right? And n is equal to 100 because our sample has n elements, right? So, in others, so you will have expected values n times p. So we have mu equal to lambda equal to 1 for our Poisson distribution, right? Then we can set up our Poisson distribution as lambda equal to 1, and basically that is the n equal to 1 to minus 1, sorry. And then we can check the two rule of thumb thing that we have to check. So first is n times p has to be less than 10. So if we multiply n times p, n is 100, p is 1/100 is 1, okay, it's passed, it's less than 10. And then we do 1,500 times p, then p already knows that is 1/100, right? This guy is 1/100. Then that is 15, and that is smaller than 100, right? So n is 100, and 1,500 p is 15. So we can say that actually the two conditions are met, and then we can use the approximation of the Poisson distribution. And so let's say that you actually are interested in having more than two defective parts. That was our idea. Then more than two, you can calculate a complement, right? Which would be having less than 2, right? Less or equal to 2. So that's what we do here. The probability of having 0 defective part, the probability of getting 1 defective part, and the probability to get 2 defective parts. And then lambda is always 1, right? And then you will get 0 factorial, 1 factorial, 2 factorial, and then the probability of getting less or equal to 2 defective parts from the 100 is 91%, and we are interested on the complement of that. So the probability of having more than 2 defective parts from a 100 sample is 0.08, very low, and that's it. You could have modeled this with a binomial distribution, but in this case it was useful for the Poisson because the probability is very low and the n is very large. Then the distribution would look like this. Again, so this is a typical Poisson distribution. You see it like that. And our average should be around 1, as we had it before. All right, with that is all. Just key points. So I repeat one more time. We talk about today distribution that model 2 outcomes, 0, 1, failure, and success. If you have only one experiment, you're talking about the Bernoulli experiment, and we know it's very simple. The mu is p, right? And then we have what happens when you repeat many times this Bernoulli experiment. Then you have the binomial distribution, and mu becomes n times p. Very simple, it's like linear. And then what happens when you have a binomial distribution that have a very low probability to happen event, and you have a large n, then it becomes problematic to calculate the binomial distribution, and you use the Poisson approximation or the Poisson distribution. And that's it. Okay? So now on, we're going to switch to other distribution. But these are very useful because usually you have these two outcomes. And it could be handy to know this distribution. It's something you can remember from this class is that this is actually the Bernoulli binomial Poisson complex, if you want to call it that, for 2 hours. All right? With that, I just shut up and thank you, and I'll see you next week.